Good evening and welcome to the 34th Jansky Lecture. The Jansky Lectureship was established by Associated Universities, Inc. to recognize individuals who have made outstanding contributions to astronomy. It is named for Carl G. Jansky, who discovered cosmic radio waves in 1933. And it's a pleasure to recognize members of the Jansky family who are with us tonight. Carl's son David, grandson Gregory, and nephew Curtis over here on that side. Tonight's lecturer is Dr. Frank Drake, research professor of astronomy and astrophysics at the University of California, Santa Cruz, and president of the SETI Institute. He is a pioneer in the search for life beyond the Earth, widely known as the originator of the Drake equation, which has played a major role in framing the discussion of the probability of extraterrestrial life. While a staff member at the NRAO in 1960, he conducted the first radio search for extraterrestrial intelligence. Dr. Drake is a graduate of Cornell University and the recipient of a PhD in astronomy from Harvard University. He shared in the discovery of Jupiter's radiation belts and conducted early studies of pulsars. He is the author of more than 150 articles and books and has received numerous honors, including election to the National Academy of Sciences and selection as a Fellow of the American Association for the Advancement of Science, the American Academy of Arts and Sciences, and the British Interplanetary Society. The title of his lecture is Progress in the Search for Extraterrestrial Intelligence. Please welcome Dr. Frank Drake.
Thank you very much, Dr. Vandenbouw, for that welcome on this occasion. And it is, for me, a very great pleasure and an honor to be here, to be selected as the Jansky Lecturer this year. It allows me to come back here to Charlottesville, where I've spent many days, in fact, over the last 40 years, and share memories, reminiscences, and jokes with my previous former colleagues and friends. Still my friends, former colleagues, at the National Radio Astronomy Observatory. It's one of the wonderful institutions in the world. It was one of the finest intervals in my life to be part of the staff of the NRAO. Tonight, I'm here to talk to you about a subject which I know interests all of you, and I think it's particularly appropriate on this occasion for the search for extraterrestrial intelligent life started at the NRAO, Dr. Vandenbouw just mentioned. It had its roots there, and the NRAO has played an important role in the research ever since. More than that, as you'll see, Carl Jansky himself had thoughts about the possibility of extraterrestrial intelligent radio signals. So in a way, he laid some of the groundwork for this subject, now 66 years ago. Well, the subject is the search for extraterrestrial intelligence, and it has to do with a subject which is of great interest to almost all human beings. We all recognize that the discovery of another civilization in space would be a momentous discovery. From it would come all kinds of very important insights and facts. Insights as to what the meaning of life is, one of the oldest of philosophical questions. What does it mean to be a human being in this universe? What may we become? What do other forms of life come to? How are they like us? Are they very different? How do they function? One of the oldest philosophical questions, also a scientific question. We also know it would be a great adventure. We see that in all of the science fiction movies. A great adventure to meet aliens from another world. One of the few great adventures left to us on Earth, now that we've explored everywhere on Earth, the oceans, and even the skies, and the nearby planets. We how those things are done, new scientific facts which would lead to a great improvement in the quality of life here on Earth. And so we know, and this has been recognized for hundreds of years, that one of the most major steps that our civilization can take is to protect another civilization. And in fact, it's an old book. You can read these thoughts from each of the philosophers on the screen I have up now. You can see that, for instance, on the left, a Roman philosopher said, "For there is such a huge supply of atoms that all eternity would not be enough time to count. There's a force that drives the atoms into various places just as they have been driven together in this world." So we must realize that there are other worlds and other parts of the universe with races of different men and different animals. And ever since we recognize that there's points of light we see in the sky at night are other suns like our own, we recognize that there was a possibility of there being life out there. Well, in science, as in life in general, wishing to make a discovery does not make it so. We have wished to discover extraterrestrial life for hundreds of years, but it has been far beyond the capability of our detection instruments to find that life. What has happened is that over the last few decades, simultaneously, scientific evidence has piled up to support the idea that there is a great deal of life in space to be found, and at the same time, the instruments which can detect reasonable signs of life have been invented and are now being exploited. And that's what I want to tell you about tonight. First, the evidence that there must be a great deal of life in space, and then how we are going about searching for it. Try to stand where I don't block these lights out. And I want to start by giving you the grand picture that we have gained as to the overall structure and history of our universe. For out of that comes the notion of the existence of life. First, we recognize that we live in a giant galaxy, the Milky Way, some 400 billion stars, some 12 billion years old, and especially amongst those stars, the sun is the most average of stars. Average in age, about 5 billion years, average in mass, average in temperature, average in chemical composition. Nothing special about our sun. In fact, if you were coming to the Milky Way from another galaxy for an interesting place to visit, probably the last place you'd pick is the sun. And of course, there's a message there. The universe is a place of great variety and a great ensemble of very fascinating phenomena, which we are probably the most fascinating we know of. And there's another important message there, and that is that, as we will see in more detail, the processes which led to the existence of the solar system, of the Earth, and the life of Earth, and even the intelligent life, were completely normal processes in the history of our galaxy. And so what happened here should have happened in many, many places. Well, to carry on with the story, we know that in the hearts of the stars over those many billions of years, nuclear reactions not only produce the energy which make the stars shine, but also the elements, the heavier elements which constitute planets and living things: iron, carbon, nitrogen, oxygen, phosphorus. And as the stars have died, they have cast this material off into space, sometimes slowly, sometimes violently, and a supernova explosion remains of one of which, a famous one, the explosion of July 4th, 1054 AD, is shown here. That material goes outwards into space, where it joins the gas and dust clouds of the galaxy, enriching them with the stuff of planets and the stuff of life. And in so doing, in a way, plants the seeds for planetary formation and eventually the origin of life itself. And we've seen a long time these gorgeous pictures from our astronomical telescopes of these great clouds of gas and dust in space. since the birth of the galaxy, and this means that all the stars born in the last 5 to 10 million years have in them, in the material that forms them, the stuff of planets and life. Well, are there planets? Some evidence for the existence of planet exists in the form of photographs such as this, similar data, which show that very young stars are surrounded by disks of dust. This is an actual photograph of the star Beta Pictoris, 54 light years from us. A young star here with its dust disk seen edge on, the light of the star itself being blotted out by a occulting disk in this nice photograph. Just in recent weeks, it's been discovered that almost all stars less than a few 100 million years old are accompanied by disks of dust. And yet, if they're older than a few 100 million years old, most of the disks of dust have disappeared. What this says is that dust disks are very common in the galaxy when stars are born, and yet they disappear. Where do they go? Perhaps they fall, the dust is blown away or captured by the star. But it is very likely that it goes to form planetary systems, which at the present time cannot be photographed by our telescopes. Well, are there other planetary systems then? One of the greatest discoveries of the 20th century has been that of the last few years, in which we have, in fact, discovered about twice as many planets outside the solar system as exist in the solar system. Some 18 such systems have been found. And interestingly, found almost, well, yes, in all cases, with old telescopes, small telescopes. In fact, almost all of them were found using the observatory you see here, which is the Lick Observatory at the University of California, just outside of San Jose. There it is. Chamber of Commerce, we never showed this slide. The tourist brochure. There's that observatory, a 100-year-old telescope in the background. In the foreground, the dome of this telescope, a 3-meter telescope, quite small by today's standards, and yet attached to it is an extremely sensitive and accurate spectrograph, which can be used to measure the positions of the lines in the spectra of stars. And those people who have done that, particularly Jeff Marcy and Paul Butler, have found that the spectral lines vary in position very slowly and by tremendously small amounts, all as a result of the gravitational pull of companions of the stars at which they've been looking. From this information, one can deduce the mass and orbits of whatever the objects are which are pulling on the planets, on the stars, and they've turned out to be, in 18 cases, planetary systems. One of the great discoveries of our century. Well, what have they found? Here is a very recent summary of all the information. And let me point out what we have here. That was pointed. Here are 18 stars. They are all very similar to the sun, and that's on purpose. That's the kind of stars they search for planets. And along the horizontal axis here, we have the distance from those stars of the objects in units of the distance from the Earth to the sun. So in our solar system, our Earth would be at this distance from the sun. And here you see all detected planets, those detected so far. These numbers here give their masses in terms of the mass of the planet Jupiter. You can notice all of them are the order of the flat mass of the planet Jupiter. And Jupiter is over 300 times more massive than the Earth. So these planets are very massive compared to the Earth. In fact, they are probably like Jupiter, great balls of gas, in fact. And that, of course, is interesting in its own right. The main point here is that there are these other planetary systems. Now, there are surprising things here. One is that all the masses seem to be so large, but that's almost meaningless because the detection techniques can only detect masses of the order of that Jupiter. It's not capable of detecting, say, an Earth yet. The other thing that's been very surprising to astronomers is that most of these, rather than being very far out in their systems, 5 astronomical units as our Jupiter is, are in very close to the star, closer in most cases than the planet Mercury is to our sun. A very surprising result, and contrary to all the expectations of theorists prior to its discovery. What does it mean? We don't know. It's thought that perhaps these planets are born far out in these systems, and because of friction within the dust disk in which these things are born, they are slowed down and move inwards into these innermost orbits. One of the most interesting is the system of Upsilon Andromedy, which is right here, which has 3 planets, as you see, showing that these really are systems with many planets, just like our solar system. This slide shows you the system of Upsilon Andromedy on the left, and the solar system on the right, to the same scale. Now note, in the Upsilon Andromedy system, there is one planet very close to the star, so you see it as a little tiny circle right here. But here are 2 others, and you can see the general pattern is very similar to that of our solar system. Again, confirming the existence of systems like our own. Now here's an interesting slight alteration in the slide we just looked at, which again gives you the Upsilon Andromedy system here, the solar system here, and up here are the actual measurements of the deviations in the spectral line positions, therefore the speed of the star either towards Earth or away from it, as observed in Upsilon Andromedy. Those variations in speed cause a Doppler effect, which is the source of the variation in the position of the spectral lines, and from that one can deduce the presence of the planets. In fact, there's one very fast oscillation here, which is given by this innermost object, which has about a 4-day period, and then you can see the next slower oscillation, which gives you this planet, and then the very slow variation, which gives you the outer planet. Now, why am I showing you this? Because on the right, we have here what you would see if you observed our solar system. If you had sensitive enough equipment, our present equipment couldn't even detect our own solar system using these same kinds of measurements. However, there are efforts underway all over the world to build better instruments, which in fact will allow us to detect systems like our own and eventually detect Earth-like planets. Well, what does that say? It says there are many, many planetary systems. Are they like our own? The jury is out on that. Clearly, many of them are not like our own. And some people have thought that perhaps that is bad news, and maybe it is, that in these systems the giant planets have gobbled up the Earth-like planets as they move in. But it may be the other way around, in fact. Here are some artists' conceptions of what you might see in these places. Here, for example, is a conception of a system where you see a star on the right, the large Jupiter-like planet on the left, and then we're reminded that if these systems are like our own, these major large planets may have systems of satellites, just as our Jupiter and our Saturn has. And those satellites themselves can be very large, of planetary size, just as Ganymede in our system is larger than the planet Mercury. More than that, if indeed these planets migrate in towards the inner parts of their systems, and this is a speculation, of course, and if they have satellite systems, the satellite systems will in fact be the first objects to encounter the material of the dust disk as they move in, and thus they may grow, and in fact become as large as planets in their own right. We would still call them satellites, but in fact they could be so large as what you see here, which is an object with ice caps. Have rings, like the planet Saturn, and if you really want to be optimistic, perhaps things like this are created in this process, where in fact enough material is captured by the planet to produce an atmosphere, oceans, and all stuff of life. We wonder about this. In any case, we do now know that there are a large number of planetary systems in the sky. If there are ones like our system, they have yet to be found. Now, another very exciting discovery of recent times has been the discovery of the Galileo spacecraft, in particular of the nature of the satellite Europa of the planet Jupiter. These are actual pictures, somewhat damaged, of that satellite. Very different from any other satellite in the solar system. As you see, I don't see, there are no craters visible on it. Simply long, straight lines and almost featureless surface, at least at this resolution. We know from the spectrum that the surface consists entirely of ice, good old ice, as we're familiar with here on Earth. And the close-up pictures of Europa show us a surface which no one had predicted. Very unusual surface, as you see here, consisting of long ridges. The scene you see here is about 5 miles across. The ridges are typically half a mile or so across, and they come as double ridges, as you see here. 2 ridges with a little valley in between. Unpredictable, still not really thoroughly explained. It's thought that these are places where the ice surface of Europa has cracked, and the fluid, which can only be water, has come up from inside and frozen to form these double ridges. It's very strong evidence, then, that there is an ocean of liquid water underneath the surface of Europa. Here's another one of these spectacular photographs. I think from everything that's been photographed in our space program, these are among the most spectacular results. These ridges, very strange features on the satellite Europa. Perhaps the most exciting of these photographs is this one here. And here we're looking at about 50 miles by 50 miles. And on this photograph, we see what are clearly ice floes, which we broke loose. One can see how they might fit together. Here's one that is broken in 2 and fits together like pieces of a jigsaw puzzle. And if you look, you'll see all over the place pieces like this one here, which move this way would match this edge here. Clearly, not too long ago, the surface partially melted, the ice cracked, and formed ice floes several miles across, as you see here. And this then is a smoking gun, which tells us that there is a liquid water body underneath this ice, and not too far down. Remember, icebergs, Titanic learned about this very conclusively. Icebergs only protrude from the liquid in which they sit by a little bit, a few percent. One can take the shadows here and measure how far they protrude from the ice. It's about a kilometer or so at best, suggesting that the ice is only about 10 kilometers thick. Well, I say only. The situation is very tantalizing. We wonder if we go through that ice and reach the ocean, will we find life in this place where nobody expected to find life, far out in the solar system where it's very cold, and yet there are the makings of life. Liquid water, heat energy from the interior of the planet, and tides, and presumably, it's yet unproven, organic compounds. What this says is that when we put it all together, is that there are more modes of life, possible abodes of life in the cosmos than we ever imagined. The universe is very productive when it comes to producing places where life might arise. But does life arise? There, we've had to depend on the work of our chemists back here on Earth, who take primordial soup. In other words, where the primordial soup comes from. And this is the stuff that chemistry created on the surface of the Earth before life developed. Organic compounds made by chemical reactions as a result of bombardment by ultraviolet light, sunlight, cosmic rays, and all the rest. And the thought is that if you take primordial soup and let it sit for 1 billion years or so, it will eventually create living things. In fact, the primordial soup is an apparatus like this. And this has been done all over the world, and what has been found is that there is a multitude of chemical pathways to the origin of life. And that's why I could say what I said a few minutes ago, and that is that as best we know, all it takes to make life is water, some organic carbon-based compounds, and sources of energy. Supporting evidence for that is the fact that there's growing evidence that the earliest living things on Earth arose deep in the sea, where it was very hot, probably due to deep sea vents. If so, that encourages the idea that life is very common in the universe, because we see things like that in such places as Europa, as we just saw, and this means that primitive life may exist in far more places than we imagined only a few years ago. On Earth, life appeared at the very earliest time they could have, about 3.8 billion years ago, and that too suggests strongly that the origins of life are easy. Now, all of that is reflects a strong consensus that there are modes of life and life where it is possible to form. Where there is a controversy is whether you produce intelligent life. And this whole subject, the only big controversy is how often evolution will actually produce intelligent species. There are those, including some eminent paleontologists, who look at the statistics and say, well, look, there have been something like 300 million species on Earth, and only one became intelligent. Doesn't that mean that the probability is very, very low? And one has to take that seriously. At the same time, one wonders if that isn't just a very basic misunderstanding of what statistics can tell you. Another statistic, which goes in the opposite direction, is the statistic on the historic size of brains in creatures on Earth. Of all the features in the fossil record, the only thing which has always increased is the size of the brain. We've had larger creatures than we've had now, faster flying creatures, we've had the great dinosaurs. All those things which contribute to survival have come and gone, but only one has always increased, and that's the size of the brain. And from that, one can argue, again, still inconclusively, that given enough time on a planet, intelligence will arise, and you will produce a creature which, if it can manipulate tools, will in turn develop technology as we have. Here's an example which supports that. This is the artist's conception of the actual dinosaur. It lived 65 million years ago in British Columbia in Siberia. Its name is Stenomygosaurus. I want you to remember that. That will never be a question on Jeopardy. It stood about our size, about 5 feet tall, it weighed about 100 pounds. It was bipedal, as you see here, and it could actually grasp things with its forepaws. More interestingly, it had binocular vision, and even more interestingly, it had a brain much larger than the typical size of dinosaur brains at this time. The typical dinosaur of this size really did have a brain about the size of a pea. They were really stupid. But not this one. This one had a brain whose size was approaching the size of the brain of a human infant. It wasn't far from having enough intelligence to be what we would call intelligent. Here's the relative of Stenomygosaurus. This one is called Sauroornithoides, which means reptile with feet like a bird. If you look at its feet, they look like the feet of a chicken, which is how it got its name. And here we see it catching its favorite meal, which were the largest mammals of its time. That was its favorite meal. And it too had binocular vision and a brain approaching the brain size of a human infant. Given a few million more years, this might have been us folks. This might have been the first intelligent creature on Earth. And this would have been your mother and your father, your boyfriend and your girlfriend. And you would have loved them just the same. These chairs would have been very uncomfortable. But that didn't happen, because before that happened, picture which is one person's conception of how that dinosaur might have evolved into a humanoid form. It didn't, because this happened at the 10-mile asteroid, came at very high speed, about 20 miles a second, and collided with the Earth. The consequence was a dreadful explosion, which raised a pall of dust which spread across the Earth in a few days. We actually know that in the geological record. A night descended on the Earth, a night which lasted not 12 hours, but several months to several years. The temperatures plummeted. In fact, the whole Earth was set on fire right after this event. The food chain was disrupted, and in the end, all of the very large creatures on Earth perished at this time. And this is a picture of a dinosaur which is realizing what's happening and is really mad. A really mad dinosaur. It was probably not a good time to be around a dinosaur, because it's not a good word at all. Well, this is when the dinosaurs were extinguished on the Earth. And what happened then was that when the sun finally came out, the creatures that could make it through the long night, by living underground in caves and holes in the ground, came out, and they found they had the whole Earth to themselves. They were the lucky ones. And they could now thrive, the great predators were gone, and 65 million years later, them is us folks. And we aren't reptiles after all. Well, that is a picture which is kind of fun to think about, and may even be true. And what it tells us is that, again, the origin of intelligence may well be a very easy one. Again, given enough time, we get intelligence. Here on Earth, once we had intelligence, in several places on the Earth independently, we developed technology, first in the form of agricultural inventions. This led to weapons development, and it was really only an instant in cosmic time, a few tens of thousands of years, 5 billion years that it took to go from primitive axes and plows to motorcycles and videotape recorders, nuclear bombs, and radio telescopes. Well, if we put all this together, the numbers that one can guess for the various things, such as the probability of the origin of life, etc. One predicts that about once per year, a new technological civilization appears in our galaxy. And that's a mind-boggling number. Once per year, it all happens all over again. Well, how many civilizations are there to be found? We recognize that a civilization like ours appears and becomes visible through its technological activities. Does this last forever? Well, maybe it does. On the other hand, maybe at least the detectability of the civilization is limited, either because the civilization destroys itself through some stupid blunder, it suffers one of these cosmic catastrophes, or more likely, at least to optimists such as myself, the civilization may be very visible for a while and then become increasingly hard to find because its ever greater prowess in technology allows it to conduct its business without creating signs of its existence. It releases less and less energy to space, and as a result becomes fairly undetectable. Well, that's the factor we know nothing about, the longevity of civilizations in detectable state. We have been detectable for over 50 years. That's all we know. Perhaps we will be detectable for tens of thousands of years, or millions of years, particularly if we're communicating with other civilizations. It's one of the great unknowns and also one of the most fascinating aspects of this whole subject. Well, how does it enter? The rate of production is 1 per year. Then the total number is, as the number of students are at the University of Virginia, the number who enter each year times the average length of time they stay. And so the number of detectable civilizations is the rate of production, about 1 per year, times their longevity. And so we get this very simple answer. If you ask the question, how many civilizations are there to find? About equal, very roughly, to their average longevity in the detectable state. Now, some of you may be wondering why this is written in fancy letters. well and why that is. It's because when you don't really know something very well in science, it makes it more impressive if you write an advanced letter. So that's why this is this way. Well, what is N? Well, we're typical. It's at least 50 years. It's probably a lot more than that. Perhaps 10,000 years. And let's just take that as a guess, if you will, in which case there are 10,000 civilizations. And of course, that's very encouraging. 10,000 civilizations to be found just in our galaxy. And actually, there are a lot more than that. Those are just the ones that we can detect. Doesn't that make it sound as though it's really easy to find them? Well, the answer is no. Because even with 10,000 civilizations, the nearest ones are 1,000 light years from us, and only 1 in 10 million stars will have detectable civilizations. Those are the challenges. For being realistic, we have to take seriously numbers like that. And it means, although we can detect signs of life, as we'll see, that we release, it may take a great deal of searching to succeed. Well, how should we search? We can contemplate looking for the lights of the cities at night. This is a mosaic of satellite photographs of the Earth at night. And if you look, you can see over on the left the outline of North America, South America. It's pretty easy to see Western Europe. You can see the outline of Spain there quite well, the various isles. On the far right, you can see Japan, which is the brightest country on Earth. The entire place is China. There's some strange things here. You see the northern lights, for example, up in the upper left-hand corner. You see some bright lights in Siberia, of all places. These are actually gas flares burning in the oil fields in Siberia. The same thing is the source of a great deal of light in Saudi Arabia. For those of you who are very good on your geography, you'll see some very bright lights just to the left of Japan, in a region which you will know is actually in the Sea of Japan. There's no city there. What is that? That is the Japanese fishing fleet, which uses very bright halogen lamps at night to cause the squid to come to the surface. And in fact, the optical, the Japanese fishing fleet is probably the prime sign of our existence. Interesting point. This is the U.S. right? It is. Let's look and see if you can find your home. It's a little hard to spot Charlottesville here, but it's there. South of Washington and west of Richmond. Well, this looks promising, but in fact, when you put hard numbers into the equations, it turns out it would take a telescope something like 5 miles in diameter to detect lights like this from a distance of 1,000 light years or so. So we don't consider this as a good option at the present time. Okay, how about rockets? Oh. E.T., Mr. Spock, Captain Kirk, they seem to be able to go from one world to another and find it takes into a commercial. Is that a good way to go? We make rockets go to the stars. Shouldn't we expect rockets to be coming to us? Well, it makes for good science fiction and delightful movies, but it doesn't make for good physics. The most speedy rockets we have now go at about a speed of about 10 miles a second. At that speed, it would take about 100,000 years to go to the nearest star, Alpha Centauri. And the nearest civilization is 200 times farther. Think about that. That's pretty impressive. Millions of years to go to where the first civilization might be, and then, of course, millions of years to come back. And your chances of actually going to the right star is only 1 in 10 million. So you've got to launch about 10 million of these missions. Have a good chance of success. Try selling that to Congress. Well, the problem there is, of course, the long time delay. But really, to use rockets, we need to go at some substantial fraction of the speed of light. Say a tenth the speed of light. Well, a tenth the speed of light is about 2,000 times faster than our rockets go now. Not 2,000 times faster. How do we do that? And you can't do it with chemistry. To achieve those velocities, you have to resort to nuclear energy. In fact, probably to the ultimate rocket, whose physics we know, although we don't know quite how to build one of these today. matter and antimatter as its fuel. Now, what's antimatter? That's ordinary matter in which the protons have a negative charge instead of a positive charge, and the electrons have a positive charge instead of a negative charge. And we've actually made some of that stuff in our nuclear accelerators, and it does exactly what was predicted, and that is when it meets matter, there's a total annihilation. Albert Einstein told us E equals mc squared, and you get an amount of energy equal to the mass of the material times the velocity of light squared. An enormous amount of energy. And it creates a great blast, a big blast, shown in this diagram. And this diagram, by the way, is cleverly adjusted so as not to let the secret out to any competitors. So it shows that the blast, the stuff that comes out of this rocket is delta rays. I don't think any of you here know what delta rays are. I hope you don't, because they don't exist. It's actually gamma rays that come out of these things. And it turns out that with such a thing, you can approach the speed of light. Easily go a tenth the speed of light. Now, as you can see, there are technical problems, such as where do you get the antimatter, and what do you make the rocket out of, which can simultaneously both matter and antimatter. We don't know what that is, but we've got a name for it. It's called mutability. So that part of the problem is solved. But even if you could solve these technical problems, it turns out to be a very daunting mission. Here's the actual design of a staged, a very economical version of one of these, designed to go at a tenth the speed of light, anywhere in the galaxy, land. You get out and take pictures and sign autographs and buy postcards and do all the things tourists do. Usually in the science fiction movies, the ETs aren't even sophisticated enough to do that. Right? So you lose all their imagination when you come to that part. You've never seen an alien buy a postcard. Science fiction movie. And this thing then can take off and return to Earth at the speed of light and land. Payload is 1,000 tons, so this thing is slightly larger than an airliner. It goes a tenth the speed of light, and the whole thing weighs 34,000 tons, about the size of a cruise ship. 33,000 tons is fuel. Half of that is antimatter. We don't know where to get that. Think about that a bit. The other half is matter. That's easy to come by. You just hook the guard goes up to that tank, kill her off. No problem at all. But the antimatter has to be made. It will take at least as much energy as is in the antimatter, and that, as you can see, turns out to be 500,000 years of the total power production of the United States. You have to close America down for 500,000 years to launch this mission, which will take 100 years to go, 10 light years. Would you want to go, by the way? Would you want to ride on an airliner for 100 years, eating airline food, watching the same movies over and over? There's a rather strange bunch of people who actually go on this mission. That's kind of the ones that you want to send. In any case, there's still other problems with this, such as when it takes off, the blast of gamma rays from this vehicle incinerates one hemisphere of the Earth. Now, there'll be a great deal of debate in the UN as to which hemisphere we give up to launch this mission. As you can see, these things are just not very promising. And it's why sending rockets does not make sense. And also why rockets arriving here on Earth don't make sense either. An intelligent civilization would not do it. The only civilization that would embark on such a mission is a dumb civilization, and they don't know how. Well, what does work? Are we quarantined from one another forever and ever? Well, in fact, Carl Jansky had an idea about that. It's hard for you to read, unfortunately, but this is the front page of the New York Times, 1933, in which they report the discovery of cosmic radio mission by Carl G. Jansky. There's K.G. Jansky there in the second headline. It's interesting that the New York Times realized this was big news. You can see it says, new radio waves trace the center of the Milky Way. Mysterious static. Reported by K.G. Jansky, said to differ from cosmic rays. Now, if you can read down the headlines, this is an eye test, folks. The very bottom headline says, only sensitive receiver is able to register. No evidence of interstellar signal. So clearly, Carl Jansky took a look at the data and wondered, is this actually perhaps a transmission interstellar? Notice, not within the solar system, but from the stars. And that was actually a justifiable question to ask because he realized that his radio emission was coming from the Milky Way and not the solar system. So it really was indicating the source of the radio emission outside the solar system. Well, back in those days, there was not equipment which could test the hypothesis that there was extraterrestrial radio waves arriving on Earth. That had to wait until the development of the National Radio Astronomy Observatory in the years 1958, 59, and in that era. Back in 59, we were building the first telescope at Green Bank. This is the one with which Shane Bottom was here tonight when I found the radiation belts of Jupiter. And this was used in the first search for extraterrestrial intelligent radios. And that came about because this telescope, utilizing the then much more sensitive radio receivers had just been invented, it could be calculated that that combination could detect signals such as we were then transmitting from Earth from the distances to the nearest stars. And so it could detect civilizations like ours. They did not have to be more advanced than we are or more sophisticated. We could detect duplicates of ourselves. And so, in fact, this was a conservative search. It didn't assume anything beyond what things we knew existed in the universe. Now, this particular picture is of the Naval Telescope at Green Bank and the people who participated in this project called Project Osmo. It's not a picture from that era, but from a picture from about 15 years ago when we had a reunion. And those of you from NRAO will recognize some of these people. Unfortunately, some of them have not passed away. This is the equipment that was used, 4 racks of equipment, monitored 1 radio channel at a time, and the data was recorded on a pen and ink recorder on the far right. Hundreds and hundreds of feet of chart paper with a red line on it. That's how the data was taken. The whole thing cost $2,000. That's what it took. And it was the start of a program which has grown and grown and grown, and is now taking place not only in the United States, but in Australia, Argentina, and Italy, and even pop up in other places. Now this was 39 years ago, and what has happened since? Since then, there have been over 60 searches, but in particular, the quality of the equipment has increased greatly. Rather than the 85-foot telescope, today we use this 1,000-foot telescope at Arecibo, Puerto Rico. Just been outfitted with a new feed system, which itself is the size of a Tato telescope. This is just to collect the radiation focused by the dish. Another 500 feet in the air, 50 stories in the air, supported by the 3 towers, which is taller than Washington Monument. This is our most sensitive telescope. It also transmits signals. It's a very powerful radar system. And in fact, that 1 megawatt transmitter creates a beam, a very highly focused beam, which to duplicate in power intensity without the big dish would require you to transmit 20 million watts. And that's equal to the total power production of all the electrical plants of Earth. Perhaps a better measure of it is that it outshines the sun, and not by a little bit, but by a factor of about 10 million at its frequency, which is about 2,000 megahertz. And so, a very powerful signal can indeed be detected by a telescope similar to Arecibo anywhere in the Milky Way galaxy. Not just at the minimum 1,000 light years, but even at a distance of 100,000 years, given the right setup of the equipment, the signal can be detected. Well, that says then that it's reasonable to search for signals from essentially anywhere in our galaxy. And at the same time, it points out how civilizations can indeed make themselves visible as we are making ourselves visible. Well, not only do we have sensitivity, but we've exploited computer technology to deal with two other major problems in the search for extraterrestrial intelligence. One is to search through all the possible frequency channels where signals might arise. We know that there's a band of frequencies which goes from about 1,000 megahertz to 10,000 megahertz, in which the universe is darkest and quietest. We exploit it to communicate with spacecraft. Other civilizations will have that same knowledge and will exploit it as we do. And thus, this argues for searching at these frequencies, which we call microwave frequencies. And so it's not that we just search the microwaves because we like to or we have good equipment for it. The universe is actually inspired to make that the most promising place to search. Nevertheless, that small piece of the electromagnetic spectrum has room in it for about 1 billion frequency channels. And we don't know which one the extraterrestrials are using, so we need multi-channel radio receivers. So that in a reasonable time, we can search through all the possible radio frequency channels. The project doesn't have one channel. Imagine how long it would take for that. Until recently, we were unable to deal with this problem, but the advent of very powerful and cheap computer electronics has given us solutions. And so today, we make special computer chips, such as this one here, which are made to perform as a multi-channel radio receiver. The first of these cost $300,000. After that, you can buy them for $50 a piece. And each one functions like a Cruz supercomputer program to do the same thing. In Project Phoenix, which is our project at the SETI Institute, we use about 47 of those chips, computer boards, as you can see here, to create a system which at present monitors 56 million channels at a time. And right now we're producing an upgraded version which will monitor 200 million channels at a time. That will be done. This is what one of these systems looks like. Still 4 racks. Always need to be 4 racks. But now it monitors 56 million channels, and more than that. Of course, there aren't enough graduate students in the world to look at the output from this thing, which is 56 million numbers a second. And so built into this is a combination of hardware and software which looks for signs of intelligent signals. That's what's here. It cost a little more than $2,000. These things now cost about $500,000. Now this does sophisticated things. I'll show you how that works. This is an old slide, but it happens to be an easy one to look at. It shows one of the monitor screens we use when we're searching. And this is presenting a part of the spectrum at which our system is looking. The horizontal axis here is frequency, and there are actually about 600 channels across there. And the vertical axis is time. Each successive line, horizontal line, needs 1 second's worth of data. So you can think of this as a plot which is showing spectrum, and then on the screen as it's changing from second to second. Where you see a bright spot is the channel that has more than the average power during 1 second, which is being presented. Now, of course, your eye sees the diagonal line, and that diagonal line is an actual extraterrestrial signal, in this case from us, from the Pioneer spacecraft. And easily detected, even though in this case Pioneer was out towards the orbit of Pluto and radiating, in this case, about 6 watts. A little more than a cell phone. Now, 2 points here. One is you see that line very easily. Our detection hardware and software can detect such lines even when they're not visible to the naked eye. The other thing you notice is the line is sloped. Now, why is that? It means that as time went on, the latest times towards the top here, the frequency from the spacecraft was getting lower and lower. Now, is that because the transmitter drifts around in frequency? No, it's locked to a measure back here on Earth. Rather, what's happening is the speed of the spacecraft towards Earth is getting less and less. The signal is getting redshifted as time goes on. Well, is that because the spacecraft is slowing down? No, it's so far from the sun that the acceleration due to the sun's gravity is trivial. What is happening is the Earth is rotating. And if you just think through the geometry, which I don't think you can do in your head, but you can usually do because of the rotation of the Earth, the speed of the telescope towards the spacecraft is continuously decreasing. As a result, the Doppler effect is introduced into the signal from the spacecraft. And we'll see in a minute, that becomes a very crucial tool in determining what signals are actually extraterrestrial intelligence signals, which ones are terrestrial intelligence signals coming from Earth. So this next one is to show you just how powerful the equipment is. This is a simulation. It's a screen just like the one I showed you, which is why I have to show you that screen. Again, frequency going left to right, time up and down. And in this case, there is a diagonal line, except the signal is pulsed, as a radar signal would be. Can you find it? Is there intelligent life in Charlottesville? This is a test. Now, I could give you an hour here, you might find it. But our equipment has to do this job in a few seconds, so it's much more later than what you see here. And I'll give you a hint. There are 5 spots that make up the signal, and they are evenly spaced. They make a diagonal line. Give you all kinds of hints. You can all have a chance here to pick out your candidate. See people guess. Really should win a prize. A Mars bar. These people who get this right. That's actually what I do in my class. They teach you Mars bars for people who succeed with this. Well, we don't have an hour here. So if this information is fed to our computer, in a third of a second produces this. Anybody get it? It's a wonderful job opportunity for you. Well, it's Mars bar. I'll go back. Even when you know where to look, it's hard to see. Sort of watching some and you can see what the challenge is. Particularly when I tell you that our 56 million channels, the total number of such screens that are actually present and could look at them is about 64,000. That's what you have to look through. Well, all of this equipment is packaged in trailers that can be taken around the world. It's been taken to the Parkes Telescope in Australia. It's been taken here. Some of you will recognize this is a 140-foot telescope that brings back one of the most recent places it's been. And there it's being used to search thousands of stars for signs of intelligent life. Right now, it is at the Observatory, and we start another run in a few weeks. And I want to show you now how powerful this search method has become, and how, in fact, we exploit the Doppler effect I pointed out to you in that previous screen presentation to identify conclusively and immediately the nature, the origin of any signal we detect. We do use the Doppler effect, and we use it, as you see here. Here's a telescope, the main telescope in one place on the Earth, the Arecibo telescope. And now, because we can afford it, and all the other projects wish they could, we're just delighted to use it. One's at Harvard and one's at UC Berkeley. Can only use one telescope. We have a second one, which is quite far from the first telescope. In our case, the second telescope is at Joplin Bank in England, a 250-foot telescope there. And there's a nice little diagram here that shows you here's the velocity of the telescope, 400 meters a second in the rotation of the Earth. And this is the component of that velocity in the direction of the star. For the second telescope, the component of the velocity you see here, and the component towards the star you can see is much less. What this says is that any true signal from space will have a different Doppler offset frequency at each telescope. And not only that, the signals will drift at both telescopes in different ways. And these offsets of drifts can be computed with tremendous precision. And so the way it works is that when we see a signal which has the earmarks of being a good candidate signal, and that happens often, because there are many, many transmitters in spacecraft, If it doesn't, that tells us right away that signal was of local origin, it's not from outer space. If it does see the signal, then we quickly compare the frequency difference due to the Doppler effect and the drift trace, and that is such a precise test that it's conclusive immediately. And in this way, we can immediately identify whether a signal is of terrestrial or extraterrestrial origin. Or I might better say human or extraterrestrial intelligent origin. So far, we have never found a signal which passed such a test. Now, here are a few examples of recent results from our present equipment. The same sort of presentation as I showed you before. Again, here's noise. Here's a very strong signal, which is that of the Galileo spacecraft. And you can see that the signal is slightly tilted towards the left, again, as a result of the changing Doppler effect. Here's another one. This is the signal from Pioneer 10 again. This can be detected by our equipment with a 100 to 1 signal noise ratio, although your eyes can, I think, barely see that diagonal line that is there. This was done when the satellite was at a distance of about 70 astronomical units, which is something like 7 billion miles, and now it's only radiating 1 watt, which is less than a cell phone, and yet easily detected and identifiable as to its origin. This is what you call an ugly signal. You know right away that one's not from outer space. Here's one of the few that got us very excited. People always ask, have you ever got something that really got you excited? Here's one. It's doing the right thing. It's drifting in frequency. Notice it's scanning back and forth in frequency. We call this the great zipper in the sky. And in fact, it got everybody very excited. It was doing all the things that was seen in both telescopes with the right offsets and all of that, at which point it set. We're left scratching our heads and wondering what to do. When it rose the next day, we were able to study it more. The Doppler drifts were not quite right. We finally discovered it was a Japanese spacecraft out beyond the moon, which we had not known about. And in fact, it's doing this funny thing with its radio transmitter because it's lost contact with Earth, and it's frantically crying help by waffling its frequency around, sort of like waving your hands, I'm here, please speak to me. That's what's going on. And this is the great DNA molecule in the sky. There's a double helix here. It's really just a result of the way we present data. And that's from a tumbling Russian spacecraft with 2 antennas on it. Give it a signal like that. Well, those are examples of what we do these days and how both sensitive we are, how much frequency coverage we can do, and how we can actually identify the sources of signal. Now, this shows the increase in capability over the years from Project Alpha 1960 to present-day Project Phoenix. This is a logarithmic scale over here. Search capability, this is a combination of sensitivity, number of channels, etc., has increased by 100 trillion times over that period. In fact, it has doubled every 235 days, and there is no end in sight. The one thing which we have wished we had, but have not had, is a dedicated telescope, so that we do not have to do our observing by being guest observers. We're getting very little time, in case of Arecibo 20 days a year, on large radio telescopes. Over the last year, we have carried out a very extensive study by an eminent group of scientists and engineers, including people from the computer industry, and out of that has come a new, what we call paradigm. That's a nice buzzword these days. These are paradigms these days. We're building radio telescopes where the goal is to achieve a great deal of collecting area, which is what SETI needs, at low cost. Now, in radio astronomy, sometimes you want to do other things, such as get high resolution, very high quality images. And then you do things like the VLA, or the proposed Alma Observatory in Chile. Our goal here is simply to get the most collecting area for the least cost. And what has been identified, with a great deal of help from our friends in India, increases with time. And the structural lifetimes are very long, 20, 30, 40 years. To take a telescope, now 40 years old. In fact, the cost of telescopes has remained roughly the same by 1 unit of measure over that whole time, which is that if you know the weight of the telescope, you can identify its cost, skip all the accounts and all that. Turns out you just take the weight and multiply it by the cost of the same weight as hamburger. And and this is a very important theoretical result, which was first established by John Finley at the NRAO a long time ago, and that's Finley's law, and it still holds. The cost of hamburgers is how you find out how much telescopes cost. Now you can see I really was. He really says what I told you to say. Telescopes cost the same as the cost of hamburgers. The second principle, which has become very evident, is the cost of electronics and computers to make systems function rapidly decreases with time. This is best expressed as Moore's law, or as one of our main supporters, which says that about every 18 months you get twice as much computing capability for the same amount of money. And this says that with the system design, you should count on it. And in fact, counted on computers as really being an operating expense, that you're going to throw them away after a few years. And so you should buy the minimal equipment at the start and assume that in a few years' time, probably by the time you have the telescope built, the computer part will be much cheaper than you imagine. Well, actually, that was recognized back in 1963 at the NRAO. It seems that much of what we have here. It's kind of fun. I've got a page which I just show the top of the page. Most of the radio astronomers here will recognize what this is just from the appearance of it. It's a page from Cruz's classic book on textbook on radio astronomy. And here on page 211, it's pointed out that one way to get a large aperture per unit cost in radio telescopes is to subdivide the single aperture into a large number of smaller apertures, such that the total aperture equals what you wanted to get in the first place. And in that case, the unit cost per aperture, or the cost of the aperture is n, which is the number of small antennas times their area divided by the cost of the electronics now that are necessary to connect these antennas together to make them all work, until they were a single large antenna. And that leads with a little trivial calculus to a formula here, which gives you the optimum size for the little antennas such that the overall cost of the system is minimal. And you get such a formula because the cost of antennas, the cost of collecting area antennas, is not linear with the area. As you put more and more area into a single antenna, the cost goes up faster than your gaining area by about the 1.5 power. And that's why you get such an equation. And it says that indeed the electronics are sufficiently cheap. You do better by connecting many, many antennas together. And here's the actual curve, which is the curve of that equation you saw, which shows you the total aperture per unit cost you get. Now, if you use antennas that are too small, the electronic cost is too great. If you use ones that are too large, the overall cost is too great because the cost of the individual antennas is now too great. From that grows the concept of achieving the large collecting area we would like to have by following that approach. Here's some actual graphs using modern data. This is for a system with expensive electronics where the cost is $1 million per antenna for everything. The receivers, electronics, and connecting cables or fiber optics to connect the system together. This is the cost of the antennas depending on their size. This is the log of the size in meters. And this is the cost of the electronics, which goes down and down because the more antennas you have, less electronics you have. The overall cost is the sum, and it gives you a curve which looks like this. Well, $1 million worth of electronics. The minimum is here at about log of 1.3, which is about 25 meters. And what this says is that, I'm not sure whether it was wittingly or unwittingly, the choice of 25 meters for the BLA was a wonderful choice. It optimized the cost of collecting it. What if you have cheap electronics? It only costs $10,000 per antenna. And we're headed that way because of the decrease in cost of computers and front ends. And you get curves like this. The minimum is here, and the log is roughly here, which is about 0.6 or so. And that suggests that you do best by using actually very small antennas on the order of 4 to 5 meters. And that has led into the concept of a telescope we now have under development for SETI, which is called the 1 hectare telescope. Its collecting area is to be 10 to the 4th meters squared, frequency covering 1 to 10 gigahertz. It has a multi-beam capability, which is, I think, is instruments give charge. And studies, such as I just sort of outlined, would suggest that 3 or 4 meter dishes will give the optimal parameter of gain divided by system noise and cost. You will need about 1,000 dishes, which is daunting but tolerable, and the total cost will be about $20 million. Now this all depends on the cost of electronics being at most a few $1,000s, including the cost of connecting these systems together. Well, part of this whole idea is based on the fact that good old American ingenuity and industry has produced very low-cost telescopes of this size. Here, you can go to a store and buy those. Complete C-band systems. Look at this. This is actually a 2.5 meter dish. And you can buy the whole system. This is retail, by the way, for about $1,000. And that includes not only a dish, but a receiver, an LNB, that's a low noise amplifier, the drive for the dish, one axis, by the way, that's all you need. A really high-quality feed horn. And it turns out these cost about $50 each in quantity. And these are dual frequency, very high efficient feed horns. And for the graduate students who have to put this together, it's even an instruction video. All for $1,000 retail. And we plan to exploit that. By the way, that industry is in need of business because the very small dishes are taken over. Now, what you do if you're just doing SETI, not trying to create a very detailed large image as you do in aperture synthesis, is you just collect the signals of all the antennas, pass them through an appropriate time delay to make up for the difference in path lengths through the geometry, use a weighting function if you want, and add all the signals together, and you synthesize a beam and synthesize the capability of a very large aperture. No need to do correlation, no need to do Fourier transforms at all. Of course, you can use the same system with correlators and Fourier transforms to create images of a very large number of pixels. But for the SETI application, you don't need to do that. And so, as I said, we're proceeding with the 1 hectare telescope. And let me just give you a very brief progress report. It turns out that really to do this well, there are a lot of enabling technologies which need to be dealt with. Identifying the inexpensive dishes, getting inexpensive low-noise amplifiers. Presently working on mimics based on indium phosphide with Sandy Weinreb in charge and funded to do that for us. You need very inexpensive cryogenic systems. Turns out right now that's the main cost problem. It's here where the big money is, and something has to be done about that. Principally, you want a feed that will cover 1 to 10 gigahertz all at once, so that you can go all over the spectrum without having to change feeds. That's a challenge. You need wideband fiber optic links, the mimics I just mentioned. You need put the RF modules on chips just to keep the price down, and then you need cheap digital signal processing computing. You already know how to do that. And plan is to use the GPS system to synchronize oscillations and timing in these systems. So far, most of this is still in the paper planning stage, in the exploration stage. The one thing which we have identified is dish. And this is one of the so-called commodity dishes made by the Orbitron company at 3.6 meters. Here it is. And it has been, this is the heart of it here, it's been modified in two ways. One is to add higher quality bearings. That increased the cost by $20. And also we had to add a declination motion to the mount. Normally we only have power in the motion, less motion. And that's achieved by using a linear actuator on a lever arm here. And that increases the price by about another $70. So in order to take the sort of thing you see in people's backyards and make it into a rugged telescope which points all over the sky with high pointing accuracy, increases the cost by $100. And you might be interested to know that the hard quotation for these antennas, dry as home, at the present time is $569 each for a 3.6 meter dish. The radio astronomy, that's pretty good. When it comes to the mimics, Sandy Weiner has already created one of them. The gain profile is good. It's good from 1 to 10 gigahertz. However, the noise level was not what was expected. There's a second attempt underway to create one with an acceptable noise level. Low-cost cryogenics, as I said, are a problem, which are a cost driver and something has to be done about. With regard to the feed, we do have a design for an ultra-wideband feed, which is a very sophisticated log periodic feed, as you see here, four-sided pyramidal shape, which will run from 1 to 10 gigahertz. The problem with it, which needs to be addressed, is that it feeds an FOV ratio of 0.69, which is quite a large FOV ratio, for which there are no commercial dishes. The hope is we can find a version of this that will feed dishes like the Orbitron dish. We're still dealing with the fiber optics, and finally we have under construction right now what we call the rapid prototype array. There's 7 Orbitron dishes with this electronic setup, which is to test the system. And one aspect of it, which is probably different from what will happen in the final stage, is that the time delay is not in here. Instead, the data is to be recorded at each dish in the RAID recording system, and these are played into a computer with appropriate time delay, just as you do in BLA, or BLE, to achieve the synthesis of the view. So that is where we stand on that, and I will finish now by showing you a couple of slides. This is an artist's conception of what the 180 will look like. There'll be about 1,000 dishes like this, as you see here. Notice it can be easily expanded by just adding more and more dishes. You don't have to start over if you want to make it bigger and bigger. So it can start as a 1 HT, but as you find the resources, make it 2 HT or 3 HT and so on, as far as your money will allow. And it will look like something like this. And this shows it to scale on a picture, an aerial photograph of the Cat Creek Radio Observatory of the University of California, which is the most likely site for its placement. So, SETI has come a long way since the start of the NRAO, since Charles Jansky thought about it, now 66 years ago, and since it's gone through this 40 years of development. I think, as you can see, it has a long way to go, and this last picture is just a symbolic one, suggesting that someday a radio telescope will find light in the sky, and that's indicated here by the organic molecule you see up on the upper right side of this picture. Thank you.
Thank you, Frank, for the fascinating lecture. I think we've filled the time here. Let me suggest that those of you who have questions you'd like to pose to Frank, meet him down in front immediately next few minutes here. And let's thank him again.